Hello and welcome once again to my channel and the ongoing series of exploring statistics for chemistry. Today is the 6th episode of the running series. Concepts and applications through problems part 2. In the part 1 earlier episode, actually you have seen that we have discussed basically basics, terminology and concepts and definitions, random errors, normal distribution, mean and standard deviation of both sample and population, and finally you have calculated the pooled standard deviation of sample. And today part 2, let me remind you again that we need to have some concepts regarding sample and population. Mean, x bar and mu. X bar is the sample mean and mu is the population. And standard deviation, again S for sample and sigma for population. And what's our target? Our target is to find the parameter value or mean of something of a population, that is mu, which we can accept as the true value or true mean value of the population. But practically because of the huge size of the population, we can't do directly, and what we do as our strategy is to find that mean and standard deviation for a smaller subset which we call the sample, statistical sample. It's slightly different from the physical sample or chemical sample, as you know, we have discussed in the last episode. So that is our strategy to apply the results that we get for sample to the population, right, which is our target. And then the question we can raise that, okay, how far the mean x bar is close to mu or S close to sigma. What about the goodness of the mean of sample or standard deviation of the sample? In other words, the question I raised that how away x bar is from mu, or in other words, can we at least fix a range around the mean within which we can say that the true or the population mean would lie in that range with, of course, a certain probability, right? So that is our target, to find the range. And we have discussed the theoretical concepts. We call it the range CI, confidence interval, and that probability with which it lies within that range is called the confidence level. And these two are of course connected. If you require high probability, then you have to compromise with the range. That means the range would be higher. And if you want a narrower range, to be more specific, then you have to compromise with the probability CL. So that we'll discuss through problems, right? And this CI and CL are connected to actually some Z and T statistic. Actually, we use Z and T alternatively if the sample statistic, suppose x bar, is a good measure of S of mu, or you can say that the sample standard deviation S is a good measure of sigma, that is a population, then we use the Z statistic, otherwise T statistics. That we have also discussed. Today we will see the problems. And finally, what is the minimum number of samples? Because you will be handling samples, not the whole population. So the question naturally arises that how many samples minimum is good enough, so that you can say that your results is approximating well the population result. So what is that minimum number of samples for desired CI with, of course, a given CL probability? So that we will discuss in today's part through numerical problems. The first question Describe in your own words why the confidence interval for the mean of 5 measurements is smaller than that for a single result. It's quite obvious and based on common sense, but the answer goes like the distribution of means is narrower than the distribution of single results. Hence, the standard error of the mean of 5 measurements is smaller than the standard deviation of a single result. The mean is thus known with more confidence than is a single result. Well, the second question, assuming a large number of measurements so that S, sample standard deviation, is a good estimate of sigma, population standard deviation. Assuming that, determine what confidence level was used for each of the following confidence intervals. So 4 intervals are given, and you have to identify that what confidence level, that means CL, was used. So it is simply you have to look at the formula for Ci, that is x bar plus minus z sigma by root n. So all these 4 expressions are given in this form, where z is this value 2.58, 1.96, etc., and sigma is of course sigma is well estimated by S, so we are using S. So z 2.52, 1.96, where from you get this z, right? And the answer is we have a table. Why this table is so, that we'll discuss in the coming slide, and we have already discussed actually. So we can say that from the z value itself, which is expressed in these expressions, z value itself, we can directly say the confidence level or probability or confidence level in percentage. Say for example 2.58, 2.58 is here, okay, so it is 99%. So the confidence interval is 99% for the first one. Similarly 1.96, 1.96 is here, so it is 95%, and 3.29 is 99.9, right, 99.9. So, and here z is 1, so for z is 1, actually it is only 68%. So that goes like that, and the finally answers are like this: 99, 95, 99.9 and 68 for A, B, C, D respectively. And one more thing, you see the relationship between Ci and Cl, confidence interval and confidence level, as I've already mentioned. And here again we see that the confidence level, if you want to increase, then Z must be increased, because higher the Z value, you see, higher the probability. So Cl increases as Z increases, and as Z increases, the range also increases, right? Plus minus increases. So the Ci also increases, and here you see the Cl and Z both, and hence Ci is in the order C highest 99.9, and then A 99, then B is 95, and then D 68. And this is the order of the Cl, right? And of course of the order of Z also, you see C is the highest one, so here you see 3.29, and then A 2.58, and then B 1.96, and then D 1. So the order is like this for both Cl and Z, and because of Z, hence Ci also. Okay, so let us go for the next slide. Discuss how the size of the confidence interval for the mean is influenced by the following. All the other factors are constant, we suppose. What are the factors? The standard deviation sigma, the sample size n, and the confidence level. So range Ci depends on all these 3. How? Okay, again you can look have a look of the expression of the formula of Ci, and that involves x mean, z, sigma, and n, all these 3. So you can easily answer the question actually, that as sigma increases, Ci increases. So here sigma is in the numerator, so sigma increases, Ci increases. And then the second question, the sample size. Okay, that is the last one. I am answering here now the confidence level. So confidence level, if you want to increase, then Z increases, as I have already seen, and if Z increases, then Ci increases. So we can ask again that how Cl and Z they are proportional. Actually, the origin you have to look at it. This is the table. From the table we can easily verify our demand, but the rationale behind it is the graph. So from normal distribution or Gaussian distribution, you see this probability is nothing but the area, and obviously if you increase the range, say here this area is minus 0.67 to plus 0.67, right, 50%. So if you increase the range, the area would increase. Area means CL, probability, and range, that is Ci. That range also increases, and because Z increases. So the relationship between or among these three is very clear conceptually also. And finally, the answer to question B, the sample size n. Here n is in the denominator. So it of course the reverse relation, that means n increases, then Ci decreases. Okay, I think you have got the point. Now let me go to the next problem. Well, there is a table. Consider the following sets of measurements. So different sets A, B, C, D, E, F. We will show only set A. So these are the values we have got, measured values, and what you have to calculate the mean and the standard deviation for each of these 6 sets, the same calculation, and also calculate the 95% confidence interval for each set of data. What does this interval mean? That we have discussed many times. Okay, so let us see how to crack the problem with the calculator. So we have taken only the A set, the results in the earlier slide. Xi values are these, and so sum over Xi is this, and we have taken the Xi square, and so that sum over Xi square is this. Why do we need? Because we have to use the formula for standard deviation, which requires these values. So the first question was for mean. So it is simply the total Xi divided by number of observations or measurements. So it is 2.86. Okay, and this is the formula that we will be using for S, that is standard deviation for the sample. Okay, so you need Xi square. So this is this one, and Xi sum then square. So that is 14.3 and square divided by n. N is 5 here, and n minus 1. You know the quotient of degree of freedom for sample calculation. So standard deviation, finally if you put the values, you will get 0.24. Okay, that is about standard deviation. But the last part of the question is to find the Ci. So for Ci, the question arises, which statistic to follow? Is it Z or T? Okay, so that you have to apply yourself. Z and T are like this, very close. Only the difference is that sigma is replaced by S. Okay, and this is called T and this is called Z. That we have seen. And accordingly, the Ci formula is slightly different in these two cases. Here Z sigma by root n, and here it is T S by root n. But T is defined in this way. Okay. The question, which one we have to use? Here the logic is that since for a small set of measurements we cannot be certain that S is a good approximation of sigma. So because we have taken only 5 measured values, so probably it would be better to go for T statistic than for Z, because S is not a good estimate of sigma, we are assuming. Okay, so the answer is we have to go for T statistic. We have to apply the formula for Ci for T statistic, this one. Okay, let us see. Well, T table we have already seen that unlike Z, where there are 2 columns, the Z values and the CL, the probability values. But here one extra column is there, degrees of freedom. So even for a given probability, if the degrees of freedom changes, then the value of T changes. Okay. So let us see. In this case, the degree of freedom is 4 because we have used 5 measurement. So 5 minus 1, 4 degree of freedom. So we have to look for degree of freedom 4 and a corresponding T value 2.78 for 95% probability. So here in the question it is 95% demanded. So we are using 2.72. So X are already known, S is already known, we have calculated, and now we can use the formula that the X bar, that is 2.86 plus minus T is 2.78 as you see for degree of freedom 4 and 95% probability by root n, and S is 0.24 that we have already calculated in the earlier slide. So the CI in this case is 2.86 plus minus 0.30. And similarly you can check the other sets results, and that is better given as an exercise, and if you are interested you can make a pause at this slide and do on your own the calculation for the rest of the sets and check how far you are right. And the last question was, what does it mean, the result? How would you interpret the result? The interpretation goes like, the 95% confidence interval is the range within which the population mean, which is the true value, is expected to lie with a 95% probability. That is the mean. That is our target also. Well, we can go for the next problem. Calculate the 95% confidence interval for each set of data in the earlier problem if S is a good estimate. So in the earlier case we assume that S is not a good estimate, that's why I use the T statistic, but here it supposes that S is a good estimate of sigma and has a value. S values are given for different sets A, B, C, D, etc. So but you have to calculate the CI, okay, with 95% CL. So again it's an application of straightforward application of the formula where X average we have already seen for this given problem is 2.86, and the formula is the same, X bar plus minus this time Z sigma by root n. So Z, if you see the table, then for 95% Z is 1.96, and for set A sigma is given 0.3, so 0.3 and by root n 5 experiment. So this is the calculation, and finally it gives you 2.86 plus minus 0.26. And you can follow the same strategy for the other sets as well. And the answers are given, you can check giving a pause if you want. So let us go for the next problem. An atomic absorption method for the determination of the amount of iron present in used jet engine well was found from pulling 30 triplicate analysis to have a standard deviation is 3.6 unit. So standard deviation, supposing that from a number of experiments you have done, you have got it. Now is a good estimate of sigma because you have done so many experiments. So it is a good estimate sigma. Calculate 95% and 99% confidence intervals for the result 18.5. That means the result, that means the true result, that means the mean X bar is given 18.5 unit. So it was based on, now only the variation is a single analysis, the mean of 2 analysis, and the mean of 4 analysis. So if I change the number of samples, right, measurement, then how you calculate? So that is box with red boundary, S is given, the probabilities are given, and the X bar is given. Okay, so let us go for the formula. It is of course Z statistic, not T, because sigma will be using because it is well estimated by the S value as it is given in the question itself. So and here is the table again for convenience, 95 and 99 we will see that it is 1.96 and 2.5. So in our calculation we will be using these two values. You see 2.58 for 99 and 95 it is 1.96. So by using the same formula you are getting the results like this. Okay, so you can check it on your own. A, B, C, all the three are given, but the problem is that a single analysis, B the mean of 2 analysis, and C the mean of 4 analysis. So here you see it is divided by root n, so it is 4 in case C. In case B it is root 2 because a measurements number is 2, and the first one root n is 1, so this is the thing. So that you have to keep it in mind carefully. Okay. A very similar problem again, S is given, and which is a spool, that means it's much expected to be much better, and that's why is approximates sigma very well, and this value is also given, the true value, that is average true, and the probability required 95 and 99%. But this time again the variation is in the number of analysis, a single, 4 and 16. So as I have mentioned, you have to just be careful regarding that value. So the same formula from table you are using 1.96 and 2.58, and here it is root n is 1, here root n is 4, and here root n is on 16, right, depending on the number of measurements. So one thing that any comment, you see that in all the cases from 95 to 99, if you increase 95 to 99, 95 to 99, the range actually increases. That is that proportional, as I have mentioned in the earlier problem. And what about the number n? As n increases, so it is inversely proportional. So in case of 16, both the results 95 and 99 are better. That means the range is smaller compared to say the case B, where it is 4 measurements. So 0.26, 0.35, and here is 0.13 and 0.17. Okay. So that is the meaningful comment you can make from this observation. Well, we are going to the last kind of problem, that is the number of measurements, minimum number of measurements needed to decrease the confidence limits for the given probabilities, of course, for the analysis described by the same problem earlier, to plus minus 2.2 unit. So we have seen in the earlier calculation that the plus minus values are 0.35, 0.17, etc., etc., which is a bit higher. Then you want it to reduce it to 2.2, plus minus 2.2. So what is the number you have to take? Number of measurements. That is the question. So again you have to use the same formula, where n is the variable actually, and z sigma by root n is actually the uncertainty region or portion, and here it is given 2.2. So 2.2 should be equal to this value, right? Now here z is given, of course, for a given probability. You can take it from the table. Sigma and n. Sigma is also given, or you have calculated, and then n is the only unknown, and that you can solve this equation to get n. So we have taken the earlier problem, S and sigma, 3.6 unit, z from the table, and n is unknown. So using that, so 2.2 is z sigma by root n, and if you simply solve for n, you will get n is 10.3 rounded to 11, and in the next case it is 18. Okay, so that means you need 11 minimum number of measurements to reduce the range to 2.2 for 95% CL, and it is 18 slightly more because it is 99% probability, right, and Z is higher. Okay. Now we will go for the similar type exercise. You can say same problem, but this time it is 0.2. So the type strategy of cracking this problem is the same. You have to look for S or sigma. It is given in the earlier problem. Z, you have to collect it from table because the probabilities are given, and you have to have the table, of course, and then only unknown is n, and you can solve for n. So you can get the results easily, 7 and 30. Please check it on your own. That would be a good practice. And this is a similar one. Sigma is 0.38. It is given. 0.38, and it is a good estimate of sigma. So we will be using the Z statistic and Z from table, and n is unknown, and there are A, B, C. Actually, the because the percentage are different, 99, 95, and 90%. So the same formula, same strategy, everything is same. You just for exercise purpose, I have included this slide, and the answers you please check on your own 11, 7, and 10. Okay. Next problem, a volumetric calcium analysis on triplicate samples of the blood serum of a patient believed to be suffering from hyperparathyroid condition produced the following data: calcium per liter. So these are the data we have produced, measurement we have produced. Now what is the 95% confidence interval for the mean of the data, assuming no prior information about the precision of the analysis? That means you are not sure whether this calculated sigma, I mean S, is a good estimator of sigma or not. And in the second case, you are assumed from your experience, maybe you have done a lot of measurements earlier, so you know that the standard deviation S is a good estimator of sigma, and that is 0.056. So in these two cases, you have to find the CI for the given CL 95%, right? So actually this problem includes both T statistic and Z statistic. In the case A, you have to use the T statistic, and in B it is the Z, because it's a good estimator, say S of sigma. So for consulting, you have to consult the table. For T, you have to be careful again for the number of measurements or degrees of freedom, etc. Because you have got 3 measurements, so it is 2, 3 minus 1, 2, right, degrees of freedom. So you have to look at the column of T value for corresponding value 2, degree of freedom value 2. But for Z, you directly get it irrespective of degrees of freedom. For 95% is 1.96. Okay. So I have already mentioned from consulting the table, and now I will be applying simply the formula. So it is x bar 3.22. It is given from the earlier problem. No, it's given here 3.22, and S is also given. So TS by root n. Here n is 3 measurement. So x bar plus minus TS by root n. So T is 4.30 as I mentioned. S is 0.06. It's given. So the answer is 3.22 plus minus 0.15 unit. And 95% CI in the other case, when you are using the Z statistic, then you see the better result, right? Because here S is a good estimator of sigma. So you are using the Z statistic, and that is nothing but x bar plus minus Z sigma by root n. So Z is 1.96, sigma is 0.06 by root n, right? So it's a good observation that how Z statistics is supposed to be better, but provided you have to have a good estimate of sigma in terms of S. Well, I will not discuss this problem in details. You just make a pause at this slide, read out the problem, the same problem, same type of problem. Here again, for the corresponding degree of freedom, you have to check what is the T value for probability 90% from the T table. And again for Z table, you just focus on 90% case, and Z is 1.64. So you can apply the same formula, and you will get the results like this. Please take it as an exercise. So today we have discussed the different types of problems, and what are the strategies for these different types, what are the inputs, what to consult the table, when to consult what table, and finally to apply the formula. So this much we have discussed in today's episode. Thanks for watching. Our next video will be coming soon, exploring statistics for chemistry part 7. And that would be statistical aids to hypothesis testing. So we'll be looking at something new. Till then, please keep on watching. Do subscribe to my channel and encourage your friends to subscribe. Thank you once again.